The question of how children learn and how best to facilitate this has been at the centre of philosophical and pedagogical debate for centuries. Figures such as Plato or Jean-Jacques Rousseau viewed education as essential to the social, moral and cultural development of children, learning which crosses traditionally defined subject boundaries forming an essential part of this. More recently, the Haddo Report of 1931 and the Plowden Report of 1967, in response to the rigidly defined subject areas found in the traditionalist approach to education favoured during the late 19th and early 20th centuries, argued that learning could not be strictly divided into neat subject categories, and instead advocated a cross-curricular approach to teaching and learning. This approach, which finds its roots in the constructivist philosophies of scholars such as Piaget and Vygotsky, challenges the traditionalist approach to education, where knowledge and skills are taught through discrete and distinct subjects, instead favouring one in which skills, knowledge and attitudes of 2 or 3 subject areas are applied to a problem, theme or idea. Following this school of thought, learning which encourages children to forge links between subjects and ideas, thus developing and deepening their understanding and constructing their own meaning, responds most naturally and appropriately to the ways in which children learn. However, it is arguable that while a cross-curricular approach based on constructivist principles best relates to the ways in which children learn, it is not without its limitations. This presentation aims to address the questions and debates surrounding cross-curricular learning through a focused analysis of the impact that cross-curricular links between science and mathematics can have on teaching and learning in a primary context. Although cross-curricular approaches prevailed for much of the mid and late 20th century, this pedagogical approach is not without its critics. One of the principal arguments against the use of a cross-curricular approach is that when divided across 2 or more subject areas, learning is more superficial or fragmentary. This has been linked to weaker subject knowledge and slower development of subject-specific skills, inhibiting children's progress. This issue has been found to be particularly problematic when tenuous links are made between subjects, for example to fit an overarching theme or topic. However, advocates of a cross-curricular approach have argued that these issues are easily addressed. Many also oppose the construction of superficial links between subjects, instead suggesting that any links made need to be meaningful for a cross-curricular approach to be effective. Moreover, such links need to be made explicit, Mujas and Reynolds stating that we don't learn facts in a purely abstract way, but in relation to what we already know. It has been argued that this can be achieved through careful focused planning, in which the use of clearly defined learning objectives and systematic reflection ensure that cross-curricular learning is given a purpose. Indeed, where careful planning for cross-curricular teaching takes place, many other benefits can be found. Most notably, a cross-curricular approach provides opportunities for children to apply skills and understanding from one area of the curriculum to another. The application of skills and understanding not only develops children's capacity for problem solving, but also deepens and consolidates learning, potentially allowing for mastery of specific skills and subject areas. Other skills and attributes can also be developed through the use of a cross-curricular approach. For example, critical thinking skills can be developed through problem-solving exercises, while many opportunities for children to develop their intellectual curiosity and inquiry skills arise, particularly when cross-curricular lessons are planned in responsive ways. In addition, the nature of cross-curricular learning, which might see greater use of creative teaching techniques, is that children are often more engaged in what they are learning and begin to take ownership of it. A cross-curricular approach can therefore be seen to develop many of the skills and attributes of lifelong learning, the approach arguably lending itself more naturally to the ways in which we as humans, and especially children, gain and apply new skills. But how effective is this approach in practice? Maths and science are subjects that are naturally linked and form what has been described as a dynamic partnership. Science makes use of mathematical skills such as counting, measurement and data handling in realising theories and relies upon mathematical concepts and language to explain and express and justify more complex ideas, such as in the field of theoretical physics. From a mathematical perspective, science provides meaning and context for the application of skills. Therefore, if real-life scientists and mathematicians rely on skills from both fields in their work, why shouldn't these subjects be taught together in the primary classroom to develop and nurture children's mathematical and scientific understanding? Indeed, various scholars have highlighted the importance for children of forging links between maths and science in order to make learning more meaningful, and to ensure that they do not view certain skills as boxed up. Moreover, the importance of making these connections between maths and science has been recognised in the 2014 National Curriculum in the guidelines for both subject areas, where the necessity of developing deeper understanding of both subjects and the role that this will play in later life is highlighted. There are numerous links to be made between maths and science at a primary level. Data handling, measurement and number skills such as counting are all important aspects of scientific inquiry and experiment, while framing these mathematical concepts in a scientific setting provides context and meaning to otherwise challenging and abstract ideas. Pattern, particularly in the natural world, ratio and proportion, and other more challenging concepts can also be explored and understanding of them enhanced through a cross-curricular approach. One of the most obvious and important links between maths and science that can be found in the primary curriculum is measurement. Measurement of time, length, area, temperature, frequency, and many other areas lies at the heart of scientific experimentation, which relies upon the development of accurate measurement skills to produce meaningful data. Scientific experiments provide obvious and practical contexts for children to practice and apply different measurement skills. If we take the common experiment of observing and measuring the growth of a plant over time, numerous opportunities exist for children to develop their skills in this area, for example measuring different parts of the plant like the stem, the area of leaves, or the time taken for different stages of growth. Making use of different forms of measurement in this way not only provides frequent opportunities for children to practice their mathematical skills, developing the importance of accuracy and precision, but also provides a focus for the observation of the ways that plants grow, engaging children in what is a lengthy and gradual process. The teaching and learning of measurement can also be enhanced through the use of ICT. If we take the example of observing the growth of a plant again, time-lapse videos provide a visual aid to learning, reinforcing aspects such as the gradual growth that children have observed over time. While useful in demonstrating the processes that have taken place, the use of ICT in this way also helps to make learning more relevant and engaging for children, and reflects the changing ways in which people are able to access and use information in the modern world. Another important area of learning that naturally falls into both mathematics and science is that of data handling. Scientists rely on the accurate collection, presentation, and interpretation of data to test and support different theories, and the development of these data handling skills is important from both a scientific and mathematic perspective in primary schools. Science provides a variety of contexts for the development of data handling skills, and it has been recognised that motivation and interest, as well as understanding, is enhanced when children are given the opportunity to collect their own data in order to answer questions they have posed themselves, as would be the case in scientific inquiry. Practicing various data handling skills and developing fluency and understanding of the processes involved also serves to enhance children's scientific understanding and reasoning, as well as providing a context for the collection of data. Graphs and charts produced can also be used to develop other scientific skills such as interpretation, analysis, and scientific reasoning. Again, such cross-curricular links can be enhanced through the use of ICT, particularly in the form of data loggers. Not only can data loggers help to provide accurate measurement of data, particularly of elements such as light levels and sound that are hard or impossible to accurately measure without them, they also open up various opportunities to further develop skills such as predicting and hypothesizing the outcome of an experiment. This is made possible by the construction of graphs in real time, broadening the teaching and learning opportunities and developing children's higher order thinking and questioning skills. Finally, drawing cross-curricular links between maths and science can enhance children's understanding of concepts that can be difficult to follow if taught discretely. Using science as a context to understanding ratio and proportion, for example the proportion of grit to sand needed to help plants to grow healthily, or the proportions of different foods that are needed for a healthy human diet, relates an otherwise tricky or abstract concept to the world around us, not only developing understanding of how ratio and proportion work, but also an understanding of their importance. Similarly, concepts such as pattern or symmetry can easily be observed in the natural world in different animals, insects, and plants. Here, cross-curricular links between maths and science help to provide an introduction to the concept of symmetry, where practical examples such as finding the lines of symmetry in different fruits allow children to explore the concept in a more hands-on way, providing opportunities to challenge misconceptions and secure understanding. However, although as naturally linked subjects there are numerous opportunities to make cross-curricular links between maths and science, it is important to note that teaching and learning has been found to be most effective when both single subject and cross-curricular learning takes place. Indeed, the discrete teaching of subject-specific skills is first necessary if the benefits from cross-curricular teaching, such as the application of skills and appreciation of the relationship between different subjects, are to be developed. Therefore, we shouldn't perceive these approaches to curriculum organisation as an option of either or, but as partners that both play an important and essential role in educating children throughout their time at primary school. In conclusion, cross-curricular approaches can be seen to develop and enhance children's learning, particularly in the areas of mathematics and science, which form a natural and dynamic partnership. There are wide and varied opportunities for children to apply and develop their skills and understanding, engage with problem solving, and cultivate an appreciation of the importance and relevance of both subjects in the wider world. This serves to deepen children's understanding, while the use of more varied teaching and learning strategies, particularly through the use of ICT, make learning more relevant and engaging for children. Therefore, the use of a cross-curricular approach to the teaching of maths and science can be seen to complement and enhance the essential knowledge, skills and understanding of both subject areas.